Hello students, today we are going to solve some typical question of real number chapter from your textbook R.S. Agarwal. The exercise 1A. Okay. So, let's start. First question, I am not going to write the question here. You can see from your book. First question is, what do you mean by Euclid's division lemma? Euclid's division lemma. Now, what is Euclid's division lemma? Euclid division lemma is, first let us know what is lemma. Lemma is a proven statement used for providing another statement. Okay. What is lemma? Lemma is a proven statement used for providing another statement. Now let's come to the Euclid's division lemma. That is, for any two given positive integers, let the integers a and b, okay, a and b, there exist unique whole numbers, such that A equals to BQ plus R, where 0 less than equals to R less than B. Here we called A as dividend, B as divisor, Q as quotient, and R as remainder. Okay, A, B, Q and R. That is, if I make it more simple for you, then it will be like this. Just remember the division. This, okay, A is the dividend, B is the divisor, Q is the quotient, R is the remainder. So what is Euclid's division lemma? For any two given positive integers a and b, there exist unique whole numbers such that a equals to bq plus r, where 0 less than equals to r less than equals to b. That means the remainder cannot be equal or greater than the divisor. Okay. Now question number 2. A number when divided by 61 gives 27 as quotient and 32 as remainder. That means divided by 61, that means divisor is 61, quotient is 27 and the remainder given is 32. Now we need to determine this dividend. Find the number. Okay, the number itself is the dividend. So we will use the division lemma of Euclid's division lemma. Okay, so let's see. So this is the dividend we need to find out. Divisor is 61, quotient 27, remainder 32. All are given. So dividend is equals to divisor into quotient plus remainder, isn't it? So divisor is 61, quotient is 27 and plus 32. So now if I multiply 61 with 27, I get 1647. Okay, plus 32. So this makes it 1679. Okay, so dividend we have determined 1679. Understood? So what we have done here, dividend. So let's therefore the required number, we will write the answer. Therefore the required number is 1679. Okay, 1679. I hope you have understood. So moving to the next question. Question number 4, 1 of 4. Okay, using division algorithm, find the HCF of 612 and 1314. We need to find out the HCF by using the division algorithm. Okay, by using the division algorithm. So first we divide so if I divide it, then two times 4 minus 4 0, 9, 90 only. Okay, so now by 90 we will divide this 600 division. So if I divide, it will be 6 times 2, then again 1 time, Then again, just we are following the division method. Okay. Now we need to write, since the question is by using Euclid's division algorithm, so we need to write here that on dividing on dividing 1314 by 612, we get quotient equals to 2 and remainder equals to 90. So therefore 1314 is equals to 612 multiplied by 2 plus 90. Okay. Then again for the second step, this is for the first step up to this division. Then for the this division, then again we will write on dividing 612 by 90, we get quotient equals to 6 and remainder is equals to 72. Therefore 612 equals to 90 into 6 plus 72. Then we are doing this. So for this we will write on dividing 90 by 72, we get quotient equals to 1 and remainder equals to 18. So therefore 90 is equal to 72 into 1 plus 18. On dividing 72 by this 18, we get quotient equals to 4 and remainder equals to 0. So therefore 72 equals to 18 into 4 plus 0. Okay. So here we will write, therefore HCF of 612 and 1314 is 18. Okay, so this is done. Next we will do question number 6. Find the HCF of smallest prime number and smallest composite number. Let's see. Smallest prime number. Smallest prime number is equals to 2. We all know that smallest prime number is 2. Okay. Then smallest composite number. Smallest composite number. Which one is smallest composite number? Smallest composite number is 4. Isn't it? Smallest composite number is 4. Now we need to determine the HCF of 2 and 4. So therefore HCF of 2 and 4 divide so therefore HCF is equals to 2. Okay, so we will write the answer that therefore HCF of smallest prime number, HCF of smallest prime number and smallest composite number is 2. Okay. Next is question number 7. For any positive integer n, prove that n cube minus n is divisible by 6. How we will do this? Let's see. How we will do this? The condition for any number, let me write the question here, that will be best. Okay, let's not write. For any positive integer n, prove that n cube minus n is divisible by 6. Okay. For any positive integer n, prove that n cube minus n is divisible by 6. Now, in order to be a number to be divisible by 6, that number should be divisible by both 3 and 2. Isn't it? The condition to be divisible by 6 is that the number must be divisible by 3 and both 3 and 2 individually. That means the number need to be divisible by 3 as well as divisible by 2. Okay. Now we need to check. whether n cube minus n is divisible by 3. Okay, first we will check n cube minus n is divisible by 3 or not. Then we will check n cube minus n is divisible by 2 or not. So let's factorize n cube minus n. If you take n common, it will be n square minus 1. Then it will be n into n plus 1 into n minus 1. Okay. When a number is divided by 3, when a number is divided by 3, then by the remainder theorem, the remainder either 0, 1 or 2. Either 0, 1 or 2. Means either 0 or 1 or 2. Okay. Isn't it? If a number is divisible by 3, then completely divisible means the remainder is 0. Otherwise, if the number is not completely divisible by 3, then the remainder must be less than 3. That is, less than 3 means 1 or 2. Okay. So, let n is equals to 3p. Okay. Let n is equals to 3p. Now, where p is a integer. P can be any integer. P is a some integer. Okay. So, or n is equals to 3p plus 1 also can be. If the remainder is 0, then n is equals to 3p. If the remainder is 1, then n is equals to 3p plus 1, or n is equals to 3p plus 2. Okay. Now, if n is equals to 3p, let n is equal to 3p, comma 3p plus 1, 3p plus 2 for some integer p. Okay. Now, if n is equals to 3p, then n is divisible by 3. N is divisible by 3. Okay. If n is equal to 3p plus 1, if n is equals to 3p plus 1, okay, n is equal to 3p plus 1, then n minus 1 is equal to 3p plus 1 minus 1 is equal to 3p. Then the number is divisible by, then n is divisible by 3. Now the question arises, why n minus 1? See here, n minus 1 is a term I have got already, okay? That's why n minus 1. If n is equal to 3p plus 2, then n plus 1 will be equals to 3p plus 2 plus 1, that is 3 into p plus 3. Then n is divisible by 3. Okay. So you can see from this that we can write so any number in the form n cube minus n is divisible by 3. Okay, that we seen. See here, n cube minus n is in factorization n into n plus 1 into n minus 1. Now all the terms are divisible by 3. Okay, so that means if I explain you in this way that 12, okay, if I explain you in this way, this, suppose I am writing 12, okay, now 12 is factorized into 3 into 2 into 2, okay. Now if only 3 is divisible by 3, that means 12 is divisible by 3, isn't it? Like here also, n into n plus 1 into n minus 1, n is divisible by 3, then also 12 means n cube minus n is also divisible by 3. N plus 1 is divisible by 3, that means also this. N minus 1 is also divisible by 3, that means also this. So this, any number is in the form of n cube minus n is divisible by 3. Now we need to check whether likewise, now check whether n cube minus n is divisible by 2. Okay, so let's check it. When a number is divisible by 2, the remainder obtained is either 0 or 1. The remainder obtained is either 0 or 1 by the remainder theorem. Okay. So, by the remainder theorem, now n is equals to 2p. N is equals to 2p or 2p plus 1 for some integer p. Okay, for some integer p. Now, if n is equals to 2p, then n is divisible by 2. If n is equal to 2p plus 1, then n plus 1 is equal to 2p plus 1 is equal to 2 into p plus 1 is divisible by 2. Okay. So we have seen, so any number in the form n cube minus n is divisible by 2. Okay. Now we will write since the given number in the form n cube minus n is divisible by both 3 and 2 individually, therefore the number will be divisible by 6. Okay. Understood? Next is question number 8. Prove that x and y are both odd positive integers, then x square plus y square is even but not divisible by 4. Now, we know that any positive integer is of the form is of the form 2q plus 1, 2q plus 1, where q is an integer, where q is an integer. Okay. So let x is equals to 2q plus 1 and y is equals to 2p plus 1. Okay, for some integer p and q. For some integer p and q. Okay, now so we have x square plus y square. X square plus y square is equals to 2q plus 1 whole square plus 2p plus 1 whole square. So this is equals to 2q plus 1 whole square is 4q square plus 4q plus 1 plus 4p square plus 4p plus 1. So this is equals to 4p square plus 4q square plus 4p plus 4q plus 2 is equals to 4 into, if I take common, then it will be p square plus q square plus p plus q plus 2. Okay. Up to this, okay? Now if I write it in this way, that here you can see that x square plus y square is even here you can see that x square plus y square is even, okay, and leaves remainder 2 when divided by 4. This, okay. Okay, so therefore we can write that x square plus y square is even but not divisible by 4. Okay. So today up to this, next day we will solve